Okay, hi, good morning. Thank you for being here. I will try to speak as loud as I can because my voice is not amplified, so I hope in the back you hear me correctly. Okay, thank you. So I'm Hugo Mercier, I'm a software engineer at IoT.BZH, and I'm going to talk about Tux-EVSE, which is an open source project for an electrical vehicle charger. So a few words about the company that I work for. So we are IoT.BZH, and we are located in Brittany, northwest of France. We are a small team of around 20 engineers with strong expertise in embedded software. We have different customers for which we do services like consultancy, support and development. And we also have a product that is called SPEC, which is both a Linux distribution oriented to embedded systems and a build platform. And so the project I'm going to present to you today is an open source electrical vehicle charger, and it has been done in collaboration with Valeo, which is car equipment supplier. And they wanted to have to showcase the possibility of an electric vehicle charger. And they also integrate a third-party commercial stack for the ISO 15118 parts. So yeah, we are focusing on the use cases that are of interest for us is based on the ISO 15118-2 and -20 standards. Which are, well, basically it's a way, as Santiago said just before, for the car and the charging station to communicate with the network protocol. So it's a TCP over IP protocol, which may involve also TLS. And it does a lot of things, but basically there are, that's a way to check that the car is authorized to charge, and a way to also check for the billing details, the payment details. So we have different modes of authentication, either with a simple RFID card that you put on the charger, or something more involved that is called plug and charge, where you have a contract with an energy provider that is stored in the car, and the car, when you plug it, will automatically, the charger will automatically check that the contract is valid and will give you access to the charging station. And it may involve lots of things online, because you have to check the contract with your energy provider, and the charger has to send details to the energy provider as well. And in ISO -20 there is also again lots of things, but one that is of interest for this project was the ability to discharge, so the car may discharge itself into the grid. So we've set up this, so we have the following setup for this project, which is quite classical. We have an embedded board, which is made basically of two CPUs, one that runs our SPEC Linux OS, and another microcontroller that runs a real-time operating system. This one is in direct contact with the electrical state of the car, and is responsible as well for handling the PWM states that Santiago mentioned just before. We also as well have a module to handle the energy measurement, something to plug an NFC card reader, and it's an internet connection, of course, and a small screen for the user interface. So the fact that we have this complex setup we may have some security issues, and at least that's we may have some security issues in the sense that it is a potential large surface of attack, because we are connected to the internet for payments and authentication. We are connected to the internal network of the car, and in itself these charging protocols are quite complex, so you may have bugs that that could be exploited by attackers. So there are some threats that exist. A simple one may be that someone find a way to charge itself freely, which is not that bad. But you may also have a compromission of a network or an electrical risk because you are delivering something that is not the right current, which may cause risks. So the design of this project has been initially thought as with security in mind, and we have been using a microservice framework that is focusing on security. It comes from Tizen, an operating system that you can find in Samsung TVs, and it's been reused also in the automotive-grade Linux project. It's basically microservices which communicate through remote procedure calls, through what we call API verbs and events. And the key point is that the different microservices are isolated one from each other, and they have all their own security context, and it's enforced by some feature of the Linux kernel that is called Linux Security Module, and especially one that is called SPEC, which could be seen as a embedded version of SE Linux, if you know. And we also have an applicative permission database that is called Synagora. So the different microservices we have for this project is these different big blocks in rows and green. So we have one that is responsible for the authentication, one for the display, one to measure energy, and one in the middle that is kind of orchestrates all the different protocols and handle all the logic of the charging protocols. And it is also connected to the power board, and it will in the end close the relay, the power connector. And we also, focusing on security led us to consider Rust as the primary language of the project. So every services that I've showed here are written in Rust because we found that it gives us memory safety without compromising performances. So we still have the core part, which is the application framework, written in C, but we have Rust binding over it. But all of the rest is written in Rust. During the development, we had to use some simulators, some car simulators, because the ISO 15118 is not simple to debug. So we have a hardware simulator which costs a lot, but we also developed an open source simulator or injector that you can find here that is able to discuss ISO 15118 if you like. So it had been of great help for the project. Yeah, so just some screens of the final product. So it reproduces the different steps of a charging sequence. So you plug your car, then it will ask for plug and charge, and if it's not available, it will fall back to it will test your authentication, plug and charge, or it will fall back to basic charging, and then give you a summary of your charging sequence. So. And that's it. So you can have a look at this GitHub page if you like. Everything is on here. So we published everything under, most of the part are Apache 2, and the core part is GPL 3 or commercial license with us. Just to give you some words about the challenges we faced. So debugging ISO 15118 was not easy. Is not easy. It's a quite complex protocol. So, as I said, having simulators and debuggers helped a lot, either hardware or software. Understanding ISO 15118 PKI. The contract with your energy provider that I told before is made of certificates, and certificates you have to have a full chain of trust to respect, and it involves lots of different actors, and it's hard to understand. And the synchronization between the different state machines of a charging sequence is not easy as well. So you have SLAC, you have ISO 15118, OCPP, and so on. So it takes a lot of time to implement and debug. And in the next steps, we would like to add so ISO-20 support to the simulator, to our software simulator, and also have an open source version of the ISO 15118 logic, which is not the case right now. And that's it. Thank you.
There's about 5 minutes if there are questions.
Yes?
What is the part in C?
What is the part in C? So the part in C, we have the part in C is what I've called the application framework, which is still in C, and then we have a binding, a Rust binding over it.
What is it needed for? What is it used for?
It's used for this microservice communications and the security layer and so on. It's still in C. Maybe one day we will port it in Rust, but it's not the case right now. And I think for the simulator part, it does not depend on this framework, but it still depends on C code that are generated automatically generated from XML schemas, and then we have Rust binding over it. And again, that's not the most direct path. We could have a direct Rust version that takes the XML schemas and directly generates Rust code. That would be a better path, I would say, but we didn't have time to do that. Yeah. Yes?
Presumably the thing you just described, where you've just got very shallow bindings for C, isn't going to introduce any significant security risk, or, I mean, there's no opportunity for a human being to foul up that automated chain of things there. That's probably the least of your worries.
Yeah.
From a security point of view, right?
If the generation chain is correct and valid, yes, that could, yeah.
Other question, next question over here.
Sorry.
Well, the parts you mentioned is a bit not straightforward to do with the ISO 15118. Have you had a chance to look at the other protocols, even though it's not applicable in Europe, but just to compare like the Chademo and the GBT to see how it is done, and if it's better, why?
Can you please repeat the question from the other?
So yeah, the question was, did we look at different protocols between the car and the charger, except the ISO 15118? I don't think we do, because that was the requirements for this project. Of course, we also do basic charging, as Santiago presented before, so the simple one with the electrical signal. But I don't even know what are the alternative.
How does this project compare to the Everest?
Good question. So the question is, how does it compare to the Everest project? So Everest is way more advanced, I would say, because it's a bigger team, but maybe this one is more focused on security. That's what we wanted to have, and that's what the final customer wanted. Yes.
I'd be interested in the differences between the hardware simulator and the software simulator, or more particularly, do you still need the hardware simulator when you have the software one?
Yes, so the software simulator is able to do, you can plug it with an Ethernet connection, so it can do the SLAC negotiation, if you're aware of that, and it can do the ISO stack, because it's only TCP communication, so it's pure software. It's okay. But what it cannot do is play with the charging state, because it's a pure electrical, and you cannot have, because the hardware part is able to also use the power line current communication and so on. So this cannot be done by software, or at least it's too complex to do.
Thank you.
Yes? Last question, I think.
Hardware available for me to just buy all of these, the charger.
So the question is the hardware available?
Yeah. Just go out and buy.
No, you cannot. No, it's not a hardware. It's not. No, you cannot buy it directly. But I didn't publish the bill of materials, but you can find it easily. I mean, it's quite available hardware that you can find. It's a FeedTech board with quite common PLC modules and so on, so you can find it easily. Thank you.